Greetings to everyone. I think we're ready to start. So, dear participants, I welcome you to our final and most probably long-awaited lecture, NeuralODE by Larisa Markeeva. A few words about the speaker today. Larisa is a PhD student at MOSCO Institute of Physics and Technology and a junior researcher at DeepTensors laboratory at Skoltech. Larisa's interests, her research interests include neural networks, numerical calculus, and tensor expansions. As a part of our online school, Larisa will talk about NeuralODE, its definition, the relationship between NeuralODE and ResNet, and their applications. I think it is true to say that in her research, she will go into the details and explain more about it. As we know, over-parameterized networks trained to convergence have shown impressive performance in domains such as computer vision and natural language processing. But unfortunately, these models have slow inference time and demand a lot of memory. Neural network compression aims to solve this issue by reducing the number of weights of neural networks using different techniques like distillation, pruning, and etc. So in this lecture, Larisa will try to consider the main approaches that are used in this field. And now, before we start the lecture itself, I remind you that please write your questions in the chat on our YouTube channel, because we're still conducting our contest for the best question. We will read them all and choose the most interesting one. Then you will have a chance to win our brand t-shirt with the MaLaHIT logo, which is quite impressive. So please try to ask as many questions as you can. We will announce the winner later, maybe today or the next day on our MaLaHIT channel. So if you haven't subscribed yet, I will leave the link on YouTube. Now, I think we can start. Larisa, if you're ready, the floor is yours.
Yeah, I think I'm ready. Hello, everyone. I think a mild misunderstanding happened. My topic today is neural network compression, so not NeuralODEs. I do apologize for this misunderstanding, but yeah, today I'm going to tell you about neural network compression. And first of all, I want to describe you why is this topic interesting and why I really like it. So the main problem here is many neural networks are really over-parameterized, and this means that they have really a lot of parameters and they could answer your questions really well. But the problem is the cost of these good answers is the time of inference and amount of memory these neural networks demand. And for example, if you have a very big neural network, you probably couldn't afford it on your mobile device, but many of our mobile devices actually use neural networks. And for, I don't know, for example, Snapchat makes their nice masks using neural networks. Speech recognition application and so on, they are all about neural networks, and hence you need to somehow adopt your high performance big neural networks for mobile devices or for other projects that have some kind of hardware or time limitations. Yeah, a brief overview of my presentation. At the beginning, I'm going to tell you about two main methods that I used in engineering to compress neural networks models. This is distillation and pruning. Then I'll tell you a bit about lottery ticket hypothesis. I'll explain you why this concept is very important. Then I present you a few follow-up papers after lottery ticket that try to address some problem that lottery ticket has. And at the final of my presentation, I'm going to tell you a little bit about more mathematical method of neural network compression. It's quite interesting subject. We are working on it a lot at my laboratory because my laboratory is about neural networks, tensor compression, signal processing, and combination of all these things. And you know, this is a very well-known thing that you can understand machine learning well only if you know math really well, because behind the hood, under the hood, we have a lot of linear and non-linear operations. And in fact, our neural networks are just a set of or sequence of linear or non-linear operations. So let's get started. Let's consider two main techniques that usually are applied in engineering. You probably are already familiar with them, but I still briefly remind you about them. So the first most popular technique is distillation. How does it work? You have two models. You have a big and very high performance model that is called teacher in this setting. And you have a smaller model that is, and it's called student. So our goal is to force our student to reproduce the function of the teacher. How can we obtain this? Actually, the idea is pretty easy. So your teacher model has some logic output at the last layer. And what do? You just enforce your student returns as similar logic output as it possible using special distillation laws. So this is the first very popular method. So you can find a lot of applications of it in computer vision, neural network, etc. It's easy, but still, while you train your model, it takes a lot of time. I mean, your student model, because your teacher first should be trained and it requires a lot of resources. But okay, let's imagine you download this model somewhere, but still you have to launch inference on this big model. So sometimes it isn't an easy story to do distillation. The second very well-known type of neural network compressing methods is pruning. So when we prune a model, we try to delete, for example, some weights or some neurons, or I don't know, even to delete a whole layer. And there are two main subtypes of these methods. This is structured and unstructured pruning. Unstructured pruning delete such units like weights, but it doesn't aim to delete a whole neuron or a whole layer. Or structured. In structured case, you try to delete a whole neuron or a whole layer. What's the difference between these two methods? The difference is quite crucial, actually, because if you delete a whole neuron, for example, you can reconfigure your neural networks, and in fact, you really will have less neurons, hence your weight matrix or tensor in this case is smaller, and you make much less operations, and hence your neural network could be trained faster or its inference is faster. But if we speak about unstructured pruning, this is a very useful concept for theory, but it isn't very useful in reality, because to launch this, the result of unstructured pruning efficiently, you need a special preprocessor that works with sparse data, and usually you don't have it. But this method, again, is very useful to, for example, to estimate the upper bound of amount of weights you can delete from your neural network without losing of accuracy. So, and actually, usually when you use unstructured pruning methods, in theory, you can delete much more layers, but in practice, you would like to use a structured pruning, and many efforts now is directed to close this gap between structured and unstructured pruning. So let's move on to the lottery ticket. I'll just present you a very brief idea of this concept. Let's imagine that we have some neural networks and we just initialize it and then we train it. Now we have a trained model and we can look into its weights. And then we prune some of these weights, for example, 20% of at each layer, just according to magnitude, to the absolute value of each weight. If it's too small, we just delete it. How do we do this? We generate a special binary mask and apply it to each layer. Then we do the following trick. We rewind our neural network to its initial state and apply this mask to weights and train again this masked model. And we obtain a new configuration of this neural network with the same architecture, but some weights are masked and some are already trained. And we got some accuracy here. And then we again look into weights and prune the smallest one, and maybe do so like 30 times. And at the end, we obtain some model that has very few weights. But the interesting thing of lottery ticket that actually you can delete approximately like 98% of weights and save your accuracy. You can look at the plot on the right bottom, and you can see we are here interested in a solid line. We can see that at the beginning we have like 97.6% accuracy, and while we were pruning, actually during some time accuracy goes up. We get even better result that we had on the full model. But after maybe the moment when we already pruned like I guess 87.1% of weights, accuracy is still more or less the same as the original model had. But after the performance of our model goes down, and that's a very interesting thing, in my opinion, that you can prune your model and in fact obtain a better result than you have. So yeah, this is actually this paper got a reward at NeuralODE 2018, I guess. So yeah, that's a very interesting phenomena, but there are plenty of drawbacks of this approach. First, that's quite obvious. If you have a real neural network, it'll take long to calculate its lottery ticket. The second one, as I mentioned, unstructured pruning isn't good enough for real-world application. It's good enough to estimate in theory how much can you prune your model, but it doesn't work that well in reality. For example, I run lottery tickets, I reproduce lottery ticket results and run a lot of trials on the neural network, and I noticed one very important thing. At the end, usually at each neuron in neural network has at least one connection with next layer. This means that I can't delete neurons from the final result, and it means that in fact I use layer matrices and tensors of the same size. So theoretically, I reduce number of weights, but in practice, it remains the same. Yeah, so, and additionally, this paper introduced the thing that is so-called the lottery ticket hypothesis. It claims, this hypothesis, that the subnetwork with accuracy like 90% out of the original, or 70 or 99% out of original, exists inside of your original neural network. One more thing about the theory that I forgot to mention on the slide, unfortunately, is that this theory actually works pretty well for small kind of toy models like LeanNet model or maybe VGG19, but unfortunately it also doesn't work that well for real world big models like ResNet 50 or something bigger. And to address all these problems, there are a few follow-up papers that try to fix all these issues like long training, unstructured pruning, works only with simple network. And I'm going to shortly go through the list of these papers, and all of them are quite interesting in terms of approach to pruning. Hope you will enjoy this. So let's get started. So I'm going to go through these models. I don't know what has happened with the numeration, I'm sorry. But yeah, all these papers are quite new. And so let's go through. The first and very interesting paper, this is a follow-up paper of the same authors like Lottery Ticket has, is about what's going on at early stage of neural network training. And actually, this paper reveals quite interesting things. For example, at the beginning, like at the very beginning of your training, like first rare actually phenomena when your weight changes side inside the neural network, but at this early stage, this happens pretty frequently. This is the first stage, and then we have the second stage. Here we are considering ResNet 20, but actually these authors showed that this kind of pictures, this phenomena, is the same for other models. So that's why these digits, I mean, the size or the number of iterations could be different, but the idea for another model will be pretty the same. So at next stage, between 10 and 500 iterations, your gradient is getting stabilized. Motions in your parameter space isn't that fast, but the performance of model is growing really rapidly, and this is interesting. Like it's going to converge, and that's why kinda your parameters are settling down at this stage. Then we go to the third stage. Oh, I can show you like this, yeah. Third stage, and here you already have roughly constant magnitude of your gradients. Weight magnitude increase linearly. Your performance is still rapid, but maybe not that much. And at this point, rewinding that I mentioned at the beginning of Lottery Ticket, it's when you take your already masked model and rewind it. I mean, set it into original state. So at this point, if you try to mask your model and rewind it back, your result will be really good. On the previous stage, if you try to do so at the previous stage, it would be less good. And then we have the final stage. So gradient are still, their magnitude, gradients magnitude is roughly constant. Weights don't change much, And performance is very close to the final value. And actually here, benefit of rewarding saturates. It means there is no many reasons to carry on with training. Even if you carry on for longer, the mask with a very high probability, the mask for lottery ticket will be pretty the same. So yeah, this is just a very interesting paper in terms of what's going on during the training. This is the third paper of the same authors, and they are trying here to address the problem that actually their approach, I mean lottery ticket, doesn't work that well with big neural networks like VGG or ResNet, etc. And according to the paper I've just mentioned, they decided to apply the following trick. They rewind their model, not to the 0th iteration, but they remember the state of the neural network at some iteration, like cath, maybe 20 iteration or something like this, and rewind our model to it, and then can fine-tune it again and prune many times. And as far as you can see, this trick works, because so we are here interested in solid orange line, and here indeed we don't lose much of accuracy, and at some point it even gets better, and then it goes down, but not as fast as model that got a rewinding to the 0 state. The same for ResNet. So yeah. One more interesting paper in terms of lottery ticket is rigging the lottery ticket, make all tickets winners. So the main idea is the following. Okay, the original lottery ticket only prunes weights, but it never recovers it. And what if we come up with some heuristic that led us to not only to prune weights, but sometimes recover them if they at some point becomes interesting for us or useful. So this idea was implemented in this paper. How do authors understand which weight is important? So in fact, they don't stop training of all weights. And if at some moment some particular weight goes above of the threshold of some value, it gets recovered. So yeah, this is how it works. Now we not only delete, but also rejuvenate some weights. And this actually showed a pretty interesting result. Unfortunately, this pruning isn't that severe like original lottery tickets. They can prune maybe 50% of all weights, but sometimes it's enough, and it also brings some improvement. For example, for ResNet, it's 0.7% better than the original model, and 1.23 times faster than the original one. Things are even better for MobileNet, but unfortunately, it works not for all models we usually have. For example, for white ResNet on CIFAR10, it doesn't work that well. Unfortunately, in their experiments, this model showed a really poor performance. So I think this is it about this paper. Yeah, this paper is also very nice, drawing early bird tickets. So the idea is the following. Okay, we have a really long training, but what if our mask that we use to mask some weights that have very small value stops changing, not at the last iteration, but much earlier. So how can we measure, how can we understand this? It's quite easy. We can, for example, measure the distance between a mask of ETH of some step and between a mask in, I don't know, car steps further. And the difference is very small. We can evaluate an early stopping. And in this case, it saves a lot of time and computation power. And yeah, this is what authors implemented. And they found that yeah, we can stop earlier, like at 20th epochs, while the original baseline has, for example, 50 or even 100 epochs. But unfortunately, pruning here again isn't that severe like original lottery ticket has. It's like usually 70% against 99.8% in the original paper. Additionally, this paper introduced a few interesting tricks I want to mention. So actually, authors showed that this approach works really well with a big learning rate. And they also try the trick that is so-called low precision training, because in general, not all neural networks need high precision computation, and this could accelerate your training pretty severely. And one more thing that they applied a special L1 regularization to patch norm layers to enforce filter sparsity. What does filter sparsity means? Let's imagine that we have a convolution. So, and this convolution has filters. And we force our model delete not a separate weight in our filter, but to delete a whole filter. This is a very nice approach, because if you zero out a whole filter, you can make your weight tensor a little bit smaller just by deleting one unit from it. Yeah, and the last paper I want to mention regarding to the lottery ticket hypothesis and follow-up papers. This is winning the lottery with continuous sparsification. Here, authors again decided to address the problem of sparsity, and that actually lottery ticket doesn't work that well on big models. And they applied a little bit another trick. So they also applied L1 regularization, but not to batch norms, but to a whole model. And additionally, they tried to use non-binary mask. And this mask help them to find kind of more important and less important weights more efficiently. And this approach actually converges faster, and lottery ticket shows up earlier in comparison with the original paper. And the interesting thing that if we look at the plot, that for example, iterative magnet pruning, this is the original lottery ticket approach here. This is a solid blue line. Here it is. You can see that actually continuous sparsification shows kind of much better performance during pruning. That's also very interesting. Yeah, but as far as I remember, what was wrong with this approach? Maybe it was long, I guess. Yeah, but in general, so there are a lot of papers that try to address this problem, but usually there is some cost of solving original problems, like less severe pruning or less accuracy, or it's hard to compute or something like this. Actually, there are still a lot of things to get done. So there is a big headroom for research, because we still can't very efficiently apply this approach to product model like MobileNet, DenseNet, ResNet, or even for big ResNets. This is the most interesting part, actually. And the second problem is we really want to kind of switch lottery ticket into the field of structured pruning, because if we found a way to apply the lottery ticket hypothesis in the sparse manner, we would have a key to efficiently cut down layers in our neural networks or cut down filters. And this will be a kind of real lossless compression of our neural networks, but we still isn't at this point, unfortunately. Yeah, but besides distillation, pruning, and I guess architecture search also counts as a compression method, there is a third approach that is about math. So you can exploit your knowledge about math and about linear operators to try to compress your neural networks models. Usually, this methods look already scary because there are a lot of, matrices, complicated words, etc. But in fact, if you get along with them well, you will understand math and machine learning and artificial intelligence much better. And the main idea of all kind of method that are applied to compress neural networks, they exploit the idea of structured data inside weight tensors. And this is quite interesting because, for example, I think everybody is familiar with SVD. So SVD has a lot of applications. For example, you can do denoising using it. Let's imagine you have a picture, and this picture is decomposed, got decomposed into the sequence of 3 smaller matrices. And middle matrix, actually a diagonal one, and it has the numbers that is called singular values on the diagonal, and they appear in this matrix in descending order. So, and now we want to delete some noise. We just zero out a few last singular values and all noise disappears. Why? Because a smaller singular value, if a singular value is responsible for very small details, and noise is a very small detail. So if you zero it out, you don't have this detail, you don't have noise. And there are a lot of interesting techniques like tensor decomposition, especially, and I encourage you to get more about them because this is a really very interesting thing that has a lot of application. And I think if you find a good tutorial about, I don't know, Tucker decomposition, tensor train decomposition, SVD, you definitely will enjoy how beautiful these approaches are. But now let's do a brief introduction about neural network compression using some crazy math. The first one, this is a very fresh paper. I think it's this year. It was published this year. It's called Eigendamage, Structured Pruning in the Kronecker Factored Eigenbasis. So there is 2 things that have been known for really a lot of years, maybe over 30 years. There are 2 approaches to prune connection in neural networks. They are called optimal brain surgery and optimal brain damage. They are very well known, but the problem was they weren't adapted for big neural networks. They worked only with small ones. But in this paper, authors offer a way to adapt this nice idea how to prune optimally some elements of our neural network for big neural networks like ResNet 50 or something like this. They also introduced a very nice idea of Kronecker eigenbasis for reparameterization of our pruned neural network. And the most interesting thing that this basis allows us to use structured pruning. So I'm not going to dive in details a lot, but just remember, there is a way to prune your models structurally using math. That's a pretty interesting point, in my opinion. So let's briefly consider the algorithm. Please not get scared. So the idea is pretty simple. We have our training data set D, and we have a pruning ratio. This how many weights we want to zero out from our model. And then we just get our weight tensor flattened and start to analyze our input data and tensor itself. So at the beginning, we compute the thing that is so-called Kronecker factors. So we have our input, and we compute a matrix A, and then we compute an expectation of actually our gradient. And this is how we obtain matrix A and matrix F. Then we can obtain our auxiliary matrices that we will use in future from these matrix A and F. And then here, the main magic happens at the line 3. We decompose our original tensor V of weights in this way, how it's showed here. And after this, we kind of go into another space, and we can assess what we want to prune in our model. And it describes, all steps are described on line from line 4 to line 9. And then to recover some loss, to recover our accuracy, we just fine-tune our model again on the same dataset. And actually, this is pretty obvious that you can do this trick a few times and obtain a very good model, but this model is pruned. Yeah, I know this algorithm looks really scary because there are a lot of matrices, etc. But if you read a paper, it's written really well. You'll get on this idea. But what does this algorithm do in reality? In reality, we have an original neural network. And for example, we have some convolutional layer, the original one. For example, here we have 101 convolution with 512 filters in and out. In the middle, we have 3x3 convolutional with the same number of channels. And at the end, we have one more. Actually, this is how this original layer was decomposed. And then our algorithm worked on it, and we obtain another set of layers that in fact represents our original convolutional layer. And you can see here that instead of 112 channels in the middle, now we have only 32. And indeed, it works much better than the original layer because you have much smaller convolutional tensor, and it works, and just math and computation over this tensor is much faster. In fact, we kind of dive into a smaller dimensional space working in, and gets better. So some dimensions of our original space got pruned. This is the first method you can apply. So yeah, instead of and it's structured as far as you can see, because we don't zero out a particular weight, but we zero out many of filters here and obtain new filters that works as good actually as original ones. This is, in my opinion, amazing. But actually not completely, this method brings not completely the same accuracy, but very close to. let's see. This is our baseline, and for example, it has 61.56 accuracy. And actually, after training, after pruning half of all weights, we lose kinda 2%, but we are still better than the rest of methods this paper is compared with. Yeah, this is quite interesting result, and of course, if you would like to, you don't have to use 50% pruning. You can use like 20%, and maybe this is enough for you, and result will be, and the gap between the original model and the pruned one will be much smaller. This is the first method I wanted to introduce you, and the second one is about crazy tensors again. So, what is neural network in fact? This is a sequence of linear and non-linear operations. So linear operation is usually followed by non-linear, like ReLU, sigmoid, or something like this. And again, you do some linear operation with the input and feed it to some non-linear function. And let's consider this weight tensor in the middle. It's pretty big. And possibly it contains a lot, maybe it has some internal structure, or it contains a lot of zeros, for example, or the same values. And you don't like it because it's big, and you want to replace it with something smaller. Because, so I don't know, you want to adapt your neural network for mobile device, and you just can't afford this big tensor here because it takes a lot of time to compute and to put it into the memory. That's why, yeah, you want to do something with it to make it smaller. And let's imagine that usual pruning and distillation just didn't work out on it. But again, this is tensor. It means that we can apply tensor decomposition to it. So tensor decomposition, it's very like SVD decomposition for matrices, but it works on multi-dimensional space objects like tensors. So actually, matrix, this is a case of tensors in 2 dimensions, and hence for SVD we have an extension for multi-dimensional space that is, and these methods are called tensor decomposition. So think about tensor decomposition now like about a black box that takes your big tensor and returns you a set of smaller ones. And if you multiply it or run over them some operation, you will obtain very the same tensor like you had at the beginning. So, and let's just feed our tensor to decomposition methods. It'll take for a while to compute the decomposition. And in final, you will obtain 2 smaller, for example, 2 smaller tensors, and you just replace the original one with this small one. And to eliminate the gap of accuracy of original model and that one you have right now, you just need to fine-tune it a little bit on the original data set. And actually, you can repeat this flow many times and compress your model more and more and more until the moment maybe accuracy drops too much and you don't want to carry on anymore with compression. But actually, this approach also has very good results. So this is a paper that was written in my laboratory. We applied this method to VGG16 and ResNet on different data sets. And you can see that drop in accuracy isn't very severe, actually. But for example, here in this string, in this line, you can compress your model 10 times and lose only 1.9% of accuracy. Actually, the same for this table, but here things are interesting. here you don't lose anything, but you get a little bit improvement of your accuracy. That is also interesting according to, for example, lottery ticket hypothesis. So we kind of get a smaller tensors that present our original one. Hence, we kind of delete some weights and delete some neurons from it because this one are smaller. But still, it works, and it works even better than original one. So yeah, it means that if you have an over-parameterized model, sometimes its architecture isn't optimal, and maybe if you kind of a bit cut it in some way, maybe delete some weights or neurons, it will be better than the original one, and the cost is like one more. You have to train it one more time, and that's it actually. So I think this is it I have for you today. Thank you.
Yes, thank you, Larisa, one more time. That was very good presentation and quite colorful, I should say.
I'm happy that you like it.
Yeah. We have one question.
Great. I can't see you. Could you read it? Maybe
yes,
I don't.
Yes.
Yeah.
I will read it to you. So the question is the following. Are there compression methods based on information theory? For example, leaving those parts of the network that process the most important information in terms of mutual information?
Yeah, there is such a paper. I can find it if a person who asks is interested in, and it indeed used mutual information, right? And there are a few other methods that try to somehow estimate the volume of information each weight or neuron carries. Yeah.
Yeah, so if you could, maybe you could leave the link.
Yeah, I need to find it. I don't remember the name on. I don't have the name on the top of my head, but I'll find it and send it to you. No problem.
Yeah, thank you. Thank you very much. So I don't see any more questions. So I guess that's it for today. Thank you very much for your time and for your great presentation. And
thanks. Have a nice day. Good evening.